If you've seen our video on SerDes, you know the AI chip race is hitting a wall. Not in the math, but in the wires. At the speeds AI now demands, copper can only carry a signal a few feet before it falls apart. So the industry is doing something radical. It is giving up on the wire entirely and moving the data onto beams of light right next to the chip. It's called co-packaged optics. And in 2026, it stopped being a lab demo and started shipping for real. This is the end of copper. Let's talk about why. Here's the setup. Every AI cluster already uses optics, fiber, and lasers to connect machines across the data center. But today, that conversion happens at the edge of the system, in plug-in modules on the front of the switch. To reach them, the electrical signal still has to crawl across inches of copper on the board, and that copper is exactly the bottleneck we keep hitting. Co-packaged optics fixes this by moving the optical engine off the faceplate and onto the same package as the switch chip. The signal turns into light almost immediately, millimeters from where it was born. No long copper run, no power-hungry chips whose only job is to clean up a fading signal. The wire problem doesn't get solved, it gets deleted. Pressure 1, power. Why move to this now? Because the old way is burning the data center alive. Each pluggable optical module sips around 30 watts. That sounds small until you realize a single large AI switch needs hundreds of them, and a data center needs thousands of switches. Added up, and optics quietly became one of the biggest power draws in the entire network. Power that does no computing at all. It just moves bits. In some of today's largest switches, the optical modules alone burn close to half of the entire box's power budget, and it gets worse with every speed bump. As ports climb to 1.6 terabits and beyond, pluggables hit a wall of heat and power they cannot cross. Co-packaged optics changes the math. By killing the long copper run and the cleanup chips, it cuts the power of each link by around 70%. That same 30-watt link drops to about 9. At the scale of a modern AI build-out, that is not a tweak. It is the difference between a data center you can actually power and cool and one you simply cannot. Pressure 2, the physics of putting light on a chip. So how do you actually move optics onto the package? With silicon photonics, a chip that does for light what a normal chip does for electrons. It has tiny waveguides that route beams, modulators that flick them on and off billions of times a second, and detectors that turn them back into signals. You build it in a regular chip fab, and you co-package it right beside the switch. But there is a catch, and it's a big one. Silicon is brilliant at steering light, but it cannot generate light. It can't be a laser. So the actual laser has to be made from a different, exotic material called indium-phosphide, and either bonded on or fed in from a separate laser source nearby. To pack in more bandwidth, several lasers of slightly different colors share one fiber, each carrying its own stream of data. Each of these optical tiles can push more than 6 terabits per second, and you stack enough of them to build one switch moving over 100 terabits. The whole thing runs so hot it has to be liquid cooled. Light is elegant. Making it on a chip is brutally hard. Pressure 3. This is real, and 2 giants are already shipping it. This is not a someday technology. Broadcom shipped tens of thousands of its first co-packaged optics switch, called Bailey, through 2025. Its next generation, Davisson, moves a staggering 102 terabits per second of optically enabled switching at roughly 70% less power than pluggables. And then there is NVIDIA. Its Quantum-X Photonics switches put the optics right on the package. 144 ports of 800 gig networking, liquid-cooled to survive the heat, available at the start of 2026, with an Ethernet version following later in the year. And it isn't only the switches. Startups like IR Labs are racing to put optical engines directly onto the GPU package itself, so light reaches all the way into the accelerator. When the companies at the heart of every AI cluster all bet their flagship products on co-packaged optics in the same year, that is not a coincidence. That is the industry collectively deciding the electrical era of the network is ending. The only question left is who controls the part that is hardest to make. Pressure 4, and this is the one almost nobody sees. We just said silicon can't make light. You need a laser made of indium phosphide, and that turns out to be the real choke point of the entire optical era. Indium phosphide lasers are extraordinarily hard to manufacture at volume and at quality. Only a handful of companies on Earth can do it. The raw indium phosphide wafers come from just a few specialty suppliers, and they are far smaller and more fragile than ordinary silicon. Coherent is vertically integrated all the way down, and it just brought online the world's first 6-inch indium phosphide production line. Lumentum is the other pillar, and right now it is the only company shipping the fastest 200 gig per lane lasers in real volume. Together, they are a near duopoly on the single component the entire shift to light depends on. And here's the tell that gives the whole game away. In 2026, NVIDIA quietly invested around $2 billion each into Lumentum and Coherent, roughly $4 billion just to lock up its future laser supply. Think about that. The most valuable company in the world spent $4 billion not on compute, but on light. So here's the verdict, and it should sound familiar. With SerDes, we found the winners weren't the chip designers. They were the handful of firms that owned the high-speed connections underneath. Co-packaged optics tells the exact same story, one layer down. The switch vendors, Broadcom and NVIDIA, will sell enormous volumes, no question. But the real choke point, the part that decides how fast the whole industry can move to light, is the laser. And the laser is controlled by two companies, Coherent and Lumentum, sitting on top of indium phosphide. They get paid no matter whose switch wins, no matter whose GPU is inside. And the clearest signal of all is the money. When Qualcomm paid billions to own a SerDes company, that told you where the leverage was in the electrical world. Now NVIDIA has paid $4 billion to lock up the lasers, telling you exactly where the leverage is in the optical one. The pattern is the same every time. The compute gets the headlines. But the boring, brutally hard upstream component, the wire, and now the laser, quietly decides whether the AI build-out can keep scaling at all. Copper is ending, light is winning, and the people who make the light are the ones to watch. If this is the kind of thing you want to understand, not the hype, but the actual choke points that decide the AI race, then this channel is built for you. We go layer by layer through how these systems really get made and who really profits when they do. SerDes was the wire. Co-packaged optics is the light. And there is a whole supply chain underneath both that almost nobody's talking about. So subscribe and stay with it, because the AI race isn't won in the compute. It's won in the connections.